For some time I'm investigating how to properly drive a gallium nitride half bridge that has two inputs, a separate input for the high and the low side. And you have to take care that when you switch between high and low, that the two FETs never switch on together, because that's bad news, right? Because then your positive power will shortcut to ground. In the previous installment I've looked at the solution that Texas Instruments uses in their reference design, and that uses an RC pair to generate that time, so to generate the time where both of the two FETs are guaranteed to be switched off. And now I'm going to use a Hercules launchpad to do the same. What we're looking after is that we should never have the two signals high together, and there should be sufficient time between one FET turning off and the other turning on. So for both sides, when you have one of the FETs switching off, the other FET should only switch on after a given time, the dead time or the deadband. So that works in the two directions. When this signal switches off, this FET switches off, the other ones should only switch on after a certain time. So this time we'll be using a Hercules launchpad, and I've already put probes on the PWM pins 16 and 17. Pin 17 is an output pin of the PWM module, and pin 16 is the component of that. So they are 180 degrees shifted in phase. When one is high, the other is low. What we want is that they don't switch together, but that for each high side there has to be a delay generated. And we'll do this step by step, because it is a bit tricky to take care that for both of the signals it's the rising edge that's delayed. So we'll start just with a plain setup of the PWM module. We have the two signals here that I'm using. I'm using PWM 1A and 1B, and we leave everything as it is. We keep 50% duty cycle. I'm not going to change that, and we don't introduce a delay. So we're starting from plain setup. I have selected here 1 millisecond as the time, the period of one signal. Normally we would be in the low nanoseconds because we would be working in megahertzes, but for this exercise it's not about the exact time and duration of the pulses. It's just that we try to take care that this pulse is delayed with a certain time, and on the other side this pulse is delayed with a certain time. We'll switch to Code Composer Studio and do a debug session, and we'll have a look on how the signal looks like. Here we can see on the scope what's happening. So we see the two signals coming out from pin 17 and pin 16. This is the PWM 1A signal. This is the inverse PWM 1B signal. And you'll see that the rising edge of this signal is exactly on the same line as the falling edge of the other system. So they're exactly each other's opposite. I'm now going to do the first changes to make that signal here take longer to go into the rising edge. So I will introduce a delay at this point. The other edge, the falling edge, will stay the same, and both edges of the lower signal will also stay the same. We turn to Halcogen to make those changes. So what we want to do is delay this edge. So we will enable delays. So we click on here, and we will say how much time, how many nanoseconds this delay will take. And normally I would put here something like 6-7 nanoseconds, because that's the expected deadband for the gallium nitride driver that I'm using. But for the sake of this exercise, where I just want to see if I can introduce a delay, I'm going to use 1/10 of the time of the full period. So our full period is 1 microsecond. I will use 1/10, which is 100 nanoseconds. We'll generate code. We'll move to Code Composer Studio and recompile, and then I'll start the debugger again and see what happens. And there we are on our oscilloscope. You see that there is more noise than there was before, and that is partly because the rising and the falling edge are not at the same time anymore. They are outside of each other, so both flanks here are influencing each other and generating some noise, while on the original setup because they were how do you call that, symmetrically in the other way, so inverse, they were biasing each other out. But we have succeeded in our exercise. We have been able to delay this rising edge of the A signal with the delay that we have entered in Halcogen, and that is 100 nanoseconds. So the falling edge is where it was before, and we were expecting a rising edge here, but that is delayed and it's only happening here. The falling edge is still okay, that is expected to happen at this time. Our next exercise will be to do the same with the B signal, so we also want to delay this rising edge here with a given amount of time. And this is where it gets tricky, so please follow along. So we want to change the rising edge of this signal, but we don't have that option because we've already consumed the rising edge delay for the top signal here. We cannot also route the bottom signal to that same delay. You'll see that it switches between those two things, so I have to choose. So the only delay that I can use is the falling edge delay, but we have a trick here. We can change the polarity of this signal so that it becomes in sync with the top signal. That means that we have the same here as what's happening on this side. That means that I can then create a falling edge delay and invert the polarity here, enable the delay, and we will have the same effect as what we had with the top signal. So instead of putting the delay on the rising edge, we invert the signal, we put the delay on the falling edge, and then we invert the signal again. And oops, I forgot to set the delay, so that can't work. So let's try this again. And here are the results. This is the delay that we introduced in the beginning. This is the time where our signals were expected to switch, but we have delayed the rising flank. Then the falling flank is happening at the time where it was expected to be, but also the B signal's rising flank is now delayed. And because of this, we are now switching on the high FET of our power driver, and at this time we are switching on the low FET, and they're never switched on together because we have this deadband introduced here. In our example, this one is 100 nanoseconds, but if we would change the time in Halcogen to be 6 nanoseconds, it would work as well. And that's what I wanted to achieve. See how easy it was to define in Halcogen and on a Hercules launchpad what the deadband of a gallium nitride driver is. And the only things we had to do was do settings in the Halcogen configurator, because in Code Composer Studio on our C code we just had to initialize the PWM module, and that's it. So I didn't have to write a line of code to tell what that deadband would be. We can now change the frequency in our code, and we can change the duty cycle, but that deadband will stay constant. So that's what we were looking after. Thanks for watching.